please. Thank you very much for the introduction. I don't need to read this slide anymore. I must say this year is much better than last year. I presented as a robot, and this is a massive improvement. At least I can see the screen. So multi-touch surfaces have provided many opportunities for collaborative work, where a number of people can work at the same time around the same surface to perform many kinds of group activities. But we lose when we have this multi-touch ability is to know who's doing what. As far as any tabletop is concerned, all touches are exactly the same, regardless of the finger, the hand, or the user doing the touch. But the question is, why do we want to know who's touching the table? Is it useful? The benefits range from benefits that relate to specific user control to application levels. So when we talk about user controls, the benefits of knowing who's doing what can range from customizing behavior of controls, such as controls that behave at the personal level rather than application level. When you talk about undo, redo, or copy and paste, we can customize the content of controls, such as showing personal bookmarks. We can also customize languages depending on user. When you talk about gestures, we are talking about interaction with objects and documents or the background of the application rather than a specific control. And again, in terms of gestures, the benefits, for example, can be restricting the interactions with a specific document, a private document, only to the owner of that document. Again, we have many examples of the benefit of identification at the application level. In the educational applications that I have developed for tabletops, I have utilized user identification to visualize participation, to enforce certain dynamics on interactions at different points in the process, and also using tagged user logs to mine for difference in behavior between higher achieving and lower achieving groups. So the benefits vary, and they are like a number of them. Then the other question is, do we need a model for user identification? What are the benefits of having a model? So these are some of the benefits that you have identified. They allow you to systematically categorize touch identification systems. They allow you to identify the common parameters for all these systems and the values for all these systems. Having done that, it makes it easier for people to specify specifications for desired systems, and having a visualization makes it easier to compare between different user identification systems or between a specific system and a set of desired requirements. So very quickly, the process for coming up with the system was an iterative one. We looked at a number of related literature that addressed this problem. We categorized the systems in these reviewed papers, and then we tried to identify the common parameters in all these papers. But this was an iterative process, so the more paper we reviewed, we used this paper to refine the model and validate it, and we go on until we moved from a simple 3-axis model to an 8-axis radar chart. So in the paper, we go through the methodology of the survey. I will not do that here, but I will just say, like, we present the model first and then use it to structure the discussion of all existing approaches or systems for user identification. So looking at a big number of, so more than 24 systems in user identification, we found out that all systems fall into one of these 5 categories, depending on the main mechanism for user identification. And these are, like, I'll start from the top, overhead camera-based systems, and these are based on computer vision to track the body and hand of users. And then we have biometrics, and they rely on, for example, fingerprints or impedance profile of users. And then we have the sensing technology inherent, and that's where the identification is built into the touch sensing mechanism, such as a system called Diamond Touch. And then we have zone-based, where identification is based on the location of interaction. And finally, we have wearables and handheld, where identification is either done through wearing a finger, a wristband, or a glove in terms of wearables, or holding a phone and interacting with the surface using the phone. As for the model itself, so it's based on like 8 main parameters that are common to all systems. I will start with surface size and go clockwise. So for surface size, all systems can either support any size of surface or are restricted in the surface size that they support, either very small or very large. And just a note for visualization, we opted for putting the values that are more flexible, more ideal towards the outer edges of this chart, and the more restrictive values towards the center. So the second parameter is infrastructure, and by that we mean, is the sensing technology, is the identification technology built into the system, or do people require external devices like wearables, or require something in the infrastructure such as cameras? And then the other one is whether the technology is independent of the touch sensing technology, or it depends on a certain technique like capacitive, or it has its own built-in hardware. In terms of user differentiation, again, systems range from being able to uniquely identify a user across multiple devices to simply differentiating between touches on the same device as belonging to different users. And then we have points of interaction, where some systems go as far as identifying or distinguishing between the hands and even the fingers of the interaction, and others only support one hand, one finger. And then we have whether the systems do that instantly or offline after the activity, or online where something in between. And then some systems restrict user mobility while others allow freedom of mobility. And finally, whether users are allowed to interact anywhere on the surface versus restricting their interaction. So the best way to explain this is to use this visualization to describe a specific scenario. So if we imagine a classroom where students work in pairs around tablets, which is a very common scenario nowadays, and the school wants to differentiate between the interaction of the different students. So students are actually accountable to what they are doing. So if we want to describe this scenario, then we'll say the surface size will be restricted to tablets. We do not need anything larger. Ideally, we do not want to use external hardware, so the technology needs to be embedded. We are working with capacitive, as like most commercial tablets. It's enough for us just to differentiate between students, student A and student B. One hand, one finger is enough for us. Any online identification is fine. Students will be seated, so we do not need mobility. And ideally, we want to be able to identify students when they interact anywhere on the surface. However, realizing that we may not find a system to do that, again, we may do some compromises. So we can say in some cases it's fine if students wear, like say, wristbands for identification, or for certain applications, it's fine if we restrict the position of interaction to a certain location, such as splitting the tablet in half. So left is student A and right is student B. So in the paper, we review 24 systems and compare them with 2 scenarios. Here, I will just go through 2 general approaches rather than specific implementation, just to give an example. So one example is camera-based systems, and there are loads of systems that fall into this category. So if I quickly go through again, starting with surface size, all these systems require large surface size. They do not work on small surfaces because they need to track big body and hand movement. The structure or the hardware is embedded in the environment. Most of them require a depth camera, a depth sensing camera, or a normal camera on top of a surface. But the benefit is that they are independent of the technology used for sensing. Most of them range between just differentiating between individuals to uniquely identifying the individual. All of them allow 2-hand, 2-finger interaction, but whether they distinguish between them or not, that's a different question. Again, all of them do online, but differ in speed. Some of them allow freedom of mobility, but many of them expect users to stand in a specific location around the surface. And finally, all of them allow interaction anywhere on the surface. So if we overlay our classroom scenario on top of that, we can quickly see that camera-based systems do not fit or do not satisfy the requirements of the classroom. For example, there is the tablet size versus large surfaces, and we do not simply want to put cameras over every tablet in the classroom, so that doesn't make sense. The second example is the most basic type of system, which is zone-based system, and that is differentiating between users based on the location of interaction. And again, if we look, these systems are starting from surface size. They need a surface big enough to allow division of the surface in territories. They do not require external hardware, and they work independent of the sensing technology, but they only differentiate between users. they assume that users are actually pressing in their own location only. They support multi-hand, multi-touch, but they do not differentiate between the hands or the touches. Instant identification, they allow students to move around the tablet, but their main limitation is they can only interact in the allocated territories. They do not have the freedom to interact anywhere. Again, if we overlay our classroom scenario on top of that, we'll see that they do not satisfy the ideal scenario, but if we accept that we limit the students' interaction in specific locations, then they will fit within the dashed region for the requirement. So it makes it very quickly to compare between what a system offers versus what we want for a certain scenario. So this is a chart of some of the systems we've reviewed, and in the paper we detail them all, but just quickly to summarize some points is there is no ideal system. Any system will have to do some compromises depending on the application required or the context of that setup. If it's in a classroom, we cannot have cameras in the roof and so on. In the ceiling, sorry. So, anyway, so for example, if we want to achieve independence of the touch sensing technology, so one option is to use the vision-based systems, but then the compromises are the need for external hardware, and the other compromise is it works only with large surfaces. The alternative is to use zone-based, and then we have the limitation of interacting only with specific locations. Other systems that wanted to achieve identifying users across devices had to rely on users' biometrics, and these can be fingerprints or impedance profiles. And in both these cases, you either require a custom hardware or require users to wear some capacitive sensing device. Again, there is always a compromise. You achieve this by doing this. So in any situation, you need to know what are the things you are willing to compromise for, and using these dimensions, it's easier to find the system that best fits your requirements. And finally, so like looking at this or summarizing the main benefits of having such a model. So first, it has a reporting power. So the terminology combined with the visualization allows designers and allow practitioners to clearly describe and report the requirements of their systems or the specification of a specific system. It has an evaluation power where it makes it easier for designers and practitioners to evaluate different systems by looking at the different parameters and the values of these parameters and whether systems satisfy them or not. And finally, it has a comparison power where it makes it easy to compare between different systems visually or between a system and a specific set of requirements. And I must say, like the visualization is designed so if a system encompasses a certain requirement, if it contains it, then it satisfies the requirement. If it doesn't, then it doesn't satisfy these requirements. So that's it. Thank you very much. Happy to take questions.
We have time for a couple of questions. I have one question. What's on the immediate horizon, do you think, of identifying users by touch?
What's the immediate horizon?
The technological horizon. So
it's difficult to tell. People are moving in all directions, so there is no one direction. So some people are still working in biometrics, others still. One thing we are exploring is using accelerometer, so you are wearing a Fitbit anyway, so we can correlate the acceleration of the hand with the touches, and then we do not need any external apart from what you are already wearing. So that's one direction we are looking at. But it's difficult to tell if anyone will actually solve it, or we'll just come up with ad hoc solutions based on specific scenarios.
Another question. It's becoming more and more popular to build multi-surface systems, so that combines interactive tabletops with other types of systems. Do you see how some of your findings could relate to that?
Yeah, so we have one of the axes. We'll just go here. The user differentiation, and we go as far as unique across devices. So whether a system achieves that or not. And the systems that do achieve that are those that require some kind of biometrics, or some systems you rely on using your own personal device. So you interact using your phone, and your phone is actually your identity. So you can move between devices. So you have to rely on something, either a handheld or the biometric. But very few systems do that.
All right, let's thank Ahmed again.